I'll stay there for now. Oh, there it's gone. All right, cool. So good morning, everybody. Welcome to my presentation on DFT investigation of the bromination of 1199 tetramethyl 9-11 teropyrenophane, which is this molecule over here. So just to recap, rho-pyrenes are a series of polynuclear aromatic hydrocarbons that start off with benzene and propagate through successive linear annulation of a phenylene unit, which is this unit highlighted in red. So the first member of the series would be pyrene, then paropyrene, teropyrene, etc. So Alexandra has already told you about cyclophanes. So if we bridge those rho-pyrenes at their most two remote positions, we can form a series of these rho-pyrenophanes. So Alexandra already told you about the pyrenophanes. Paropyrenophanes have not been synthesized yet. And in our group, we have synthesized a number of teropyrenophanes. And one of the teropyrenophanes that have been synthesized on the gram scale is this huge structure that I will be calling from now on the teropyrenophane for the simplicity. So this structure has been synthesized on gram scale, as I have already mentioned. So this allows us to do some interesting chemistry with the structure. And one of the first things that has been attempted on this teropyrenophane is the bromination reaction. So this tetrabromination reaction occurs quantitatively at very mild conditions in dichloromethane. And ever since it has been published in 2018, our group's efforts have been focused on investigating this transformation. A lot of analysis have been done on this structure already. However, when DFT investigations were attempted, from my understanding, they failed. So given the situation with the labs and COVID and my own personal situation, I decided to give this old computational project a go. So why would we want to study this system with DFT anyways? So as Alexandra has already told you, DFT can be used to study strain energies for structures and stuff like that, but it can also be used to study the reaction pathways mechanistically. So to search for transition states, intermediates, species like that. So the teropyrenophane is a aromatic system. However, it also has these regions that are called the K regions, and those are olefin-like in nature. There's a question of whether this bromination occurs via electrophilic aromatic substitution or olefin-like bromination, and this is something we're going to be talking about today. So first things first, we had to simplify this structure from the huge the teropyrenophane to the 2,11-dimethyl teropyrene. And this was done for the purposes of reducing computational cost, as this structure is very computationally complex to process. They still have the same K regions, so the system should have the same reactivity. Another assumption we had to make is come up with the guess for the transition state, which is arguably one of the most difficult parts of this whole DFT investigation process. And in order to do that, we had to guess the mechanism for our structure. So once again, we've talked about electrophilic aromatic substitution. There's also olefin-like bromination. And we've just decided to pick olefin-like bromination just for the sake of it. So this is usually what the olefin-like bromination is believed to occur via this energy diagram, even though recent publications suggest that this is a much more complex molecule, a much more complex system. But usually in second-year organic chemistry textbooks, this is the energy diagram that we're given. In any case, it usually occurs through this bromonium ion intermediate. So the first transition state here should resemble in geometry to this first intermediate, however, not exactly be that structure. So to get a feel for what our transition state should look like, we've modeled a simple DFT bromination of an ethene molecule. And this is the structure, the transition state structure that we have obtained for Bethrelip 631G level of theory, which is a reliable level of theory for geometry optimizations and stuff like that. So as we can see, the distances between this bromine atom and the reactant carbon atoms are pretty much the same. It's 2.4 and around 2.6 angstroms, which suggests that the next step in this bromination reaction is the formation of the bromonium ion intermediate, where these distances are the same. Another interesting thing we can notice is that this bromine prefers the sideways orientation, even though the bromination was modeled perpendicular to the plane of the molecule. And this trend is something that we'll be seeing future with the other transition states. Okay, moving on, extrapolating that structure that we've obtained for the ethene. This is the structure that we obtained for our model compound. The transition state structure at the Throlip 321G level of theory, which is a slightly lower level of theory than the one that we talked about previously. But in any case, it is a transition structure, transition state structure. So how do we know that this is actually the transition state and not some other random species in our mechanism? So transition state structures have something that's called an imaginary frequency, which is an IR frequency that can only be detected via computational methods because it's technically negative. And so the imaginary frequency for this structure, this specific level of theory, was determined to be around 125 I reciprocal centimeters. So now that we know that we have obtained the transition state, to confirm the authenticity of this transition state, we need to run intrinsic reaction coordinate calculations. And this is what usually the IRC plots should look like. Those are plots of decreasing, gradually decreasing energies. And this calculation allowed us to confirm that this is, in fact, the transition state that we were looking for that specific system. So moving on, higher levels of theory. The structure was obtained with higher levels of theory, gradually to 631G, we already talked about, CCPV to Z, and finally DEF2 triple zeta VP, which is a very reliable basis set to study those types of systems. And this is the transition state that we've obtained for the bromination of the planar model compound. So now onto probably one of the most important parts of this project is looking at the structure and trying to figure out what's going on. So first things first, we can notice that distances between this bromine atom and the reactant carbon atoms are not the same as we were expecting for the olefin-like bromination. So there's a stronger interaction between this bromine atom and this carbon atom, and the distance is 2.2 angstroms. So this suggests that this is more along the lines of electrophilic aromatic substitution. And also this confirms the experimental results for the bent counterpart, because this is where the bromination actually occurs. Another thing, once again, noticeable is that the bromine once again prefers the sideways orientation, and there is an interaction, a van der Waals interaction between the departing bromine atom and the hydrogen atom on the neighboring K region. We believe this might have some stabilizing effect on the transition state. However, those claims are too bold to make right now. Another notable thing is that the planar system undergoes a little bend once the bromination occurs. So we decided to measure this bend by measuring the dihedral angle between this plane and the plane of the bend. And it looks like with the increase of the level of theory, this bend kind of straightens out, which makes sense. Another very important thing to mention is that regardless of the level of theory, the structures look pretty much the same. There are no observable trends in the geometries, which allows us to argue that the IRC calculations obtained at the lower level of theory are enough to confirm the authenticity of the transition state, and we should not repeat those calculations at higher levels of theory. What matters, however, on the higher level of theory is the energy. The energies at the lower levels of theory are not very reliable for those types of computations. However, at DEF2 triple zeta VP, it was possible for us to construct this energy diagram. So this is the starting material obtained from the IRC. This is a transition state that we've seen already. And this is supposedly the final product. And there's obviously a whole bunch of steps in the middle, but we're just considering the first transition state for now. So the delta G of the reaction is a negative value, which suggests that the reaction is favorable in the forward direction, which makes sense. The activation energy is very huge. It's 146 kilocal per mole. And this huge overestimation is mainly attributed to the fact that this is a planar system and the reactions were performed in gas phase. We expect much lower numbers for the bent counterpart and in the solvent system. So moving on, once again, taking the structure that we've already obtained, extrapolating it on the structure of interest, we obtained this transition state for the teropyrenophane structure, which is pretty exciting. So once again, there's a notable smaller interaction between this carbon atom and this bromine atom. In fact, this distance here, 2.2 angstroms, is smaller than for any of the previously mentioned planar systems. So this suggests that this bromination for the benzene counterpart is more favorable than for the planar counterpart, which once again makes sense. And more water. Once again, the bromine here is in its sideways orientation. However, there is no van der Waals interaction with this neighboring proton, but there is a similar interaction between the departing bromine atom and the proton on the K region that's undergoing the attack. And once again, there's pretty much no strain. There's no bend in the system because the molecule is already bent, and this once again suggests that this bromination is much more easier than for the planar system. So in conclusion, DFT calculations were performed on the teropyrenophane, and the transition states TS1 prime, TS1 were obtained. Despite their differences, the simplification for the planar system was an important step in this investigation, as it provided the initial guess for this transition stage, which is arguably one of the most important steps for the further development of the project. Some things we might consider doing next is optimizing this structure at high levels of theory, as well as optimizing both of those in the solvent systems. And this is pretty much all from me. I would like to thank my supervisor, Dr. Graham Bodwell, for his assistance and support, as well as Dr. Yuming Zhao and Dr. Erica Rashad. And I would like to thank you, my audience, for your attention. If you have any questions, please fire away.
Start off with student questions. That was a great talk. Thank you so much.
Thanks.
Questions? You mentioned during your talk the grams.
Right. Yes. No, we have obtained this structure here. I believe it was like a gram of material that we could obtain. Yes, yes, yes. No, I did do this synthesis as my summer project. So you can have a lot of it if you use a lot of starting material. Yeah.
Okay. Not undergrads on the
Yeah.
So mentioned during the talk.
Right. The transition state energy would be much lower, or rather this gap, the activation energy. Because this system, when we ran the reaction, when we actually did the reaction, not computationally, but physically, this is a very fast reaction. It only runs for like 30 minutes, maybe less, but 30 minutes is what we believe it is. So we presume that this gap should be much, much lower, like around actually 5 kilocal per mole, maybe. So that's just the kinetics of it.
What can I count?
Right, because this was run in the gas phase, because that's what you usually do. You start with the gas phase and then you optimize for the solvent system. The solvent is supposed to minimize this energy because if you think about it, this reaction in the gas phase would take much, much slower, and this probably wouldn't even occur. And this is something we can only measure computationally. You know what I'm trying to say? Do I answer your question? Okay. That's probably in the beginning, and this is just usually what is taken from
I guess
chemistry textbooks. Well, yeah. Yeah, probably. Once again, like solvent effects, this isn't something that we have investigated yet, and this is something I would like to look at. But yes, I think I know what you're trying to say. Like the solvent would stabilize the charges in the transition state. Probably. I'm not sure, honestly. Cannot answer that with 100% certainty.
Go for it. So how do you, I don't know if I'm phrasing this question, but how do you know when you're actually in the transition state? Because if you think about a reaction, I bring two molecules in together, they do something and then they separate. So
Right.
where do we call it a transition state? Because it's as soon as the reaction is starting, you're inside a transition state.
Right. So, for example, this is the bromonium ion intermediate, right? So we might measure the distances between these two atoms, this carbon and this bromine, and they should be pretty much the same. But for the transition state, this would resemble this structure here. However, the distances would be bigger since there is like this bromine is still approaching. It's not exactly bonded yet. So there will be like those dashed bonds there. So that would be the transition state. Am I?
But at which distance, I guess, if it's constantly coming closer and closer and closer,
Yeah.
is this a transition state? Like, so let's say the bond is here. Is this a transition state? Is this, it's this, or like, so where do we say we've reached a transition state versus we've reached an intermediate?
Right, and this is a good question because this is what makes the DFT calculation so difficult. You need to guess this distance very precisely because if you guess it a little bit farther, it's not a transition state. It's just like bromine and your reagent. But like you got to guess the distance like very, very precisely. Right, so like 2.4. I believe the distance of the I'm not gonna guess. No, I'm not gonna guess that. I'm not gonna even try that. But you know what I'm coming from? Okay.
Sort of, if you think back to the question about the charge stabilization, what solvents are
Well, for this specific system, this is just dichloromethane. But usually, when you run computations of those types of systems, it's usually dichloromethane or chloroform. So you wouldn't actually see any like charge stabilization because those are not what that's for. Stuff like methanol, stuff like that. So.
dichloromethane, chloroform certainly.
Yeah. Right.
Let's thank our speaker. I think that ends our morning session. Let's thank all of our speakers. One more session this afternoon at 2 o'clock. If you don't have the link, send me an email. I will probably, as I walk back to the department, I'll let Debbie know to send it out so everybody has it. But otherwise, thank you everybody for joining us for the 490Bs. Looking forward to the 490s next year as well. Thanks, everybody.